Okay, I think we can start. So, welcome to the last day of the summer school. So this morning we have again Professor Witt, who will continue his lectures on elliptic boundary problems for edge-degenerate pseudodifferential operators.
Thank you very much, and good morning, everybody. Last round of the summer school. Just let me remind you what yesterday. So the result was basically calculus for cone-degenerate operators on the half-line. For the form, now this is called T, for T is called S, and geometric properties are like that. Plus, then we have here a number of boundary conditions and S minus delta Q plus. Yeah, and P and Q were described types. The types for asymptotic expansions of photomultiply as x goes to 0. That's the types of these types for asymptotic expansions of normal type as x goes to 0. And x was a variable. Yeah, and the point was prescribed. So, and then maybe I should have made it clear. I said it yesterday. So, if you are only interested in the Fredholm property, you are good here with corner. This operator, yeah, the ellipticity of that operator A. Okay, curly A only depends on A. On that guy. So yeah, if that is elliptic, then the mapping from here to here is a Fredholm. So assuming suitable conditions imposed at x equals infinity, which I did not discuss, but then actually we filled up the whole thing with boundary conditions and co-boundary conditions to get the whole thing invertible. And this is why in our edge calculus, the operators have boundary symbols, and boundary symbol takes values in that calculus. And so basically then it becomes part of the ellipticity condition that these boundary symbols are pointers invertible. So basically for later we have these. So basically here's a good thing. We have to fill out things to two mappings. Okay. So now we have the cone calculus. Now how to go on and just pass to the. Maybe I can. No, I cannot. I just have to scroll through, right? It was a little bit far. Okay, so what is so how to pass now to the higher dimensional situation? Let me remind. What? Now the operators are of that form, so formally. So the A is the differential operator is something like that. So this was the variable normal to the boundary, so sort of measuring the distance to the boundary. And this was the tangential variables. The operator close to the boundary can be written in that way, where m is the order of the operator. So now we need an idea. And basically that is a really original idea. It is abstract edge calculus. It looks very simple, but it can be applied in many situations. Not just in that one and that one. Okay, so what does edge philosophy mean? Certain strongly continuous group actions get involved. So how is that? Yeah, so basically the local model of an edge is a cone bundle over that edge, and then basically if you have also cones here, so we have a stretching in the radial direction, and this gives us the group actions. So the definition works for some abstract group action, and it is as follows. So we start with a Hilbert space. It is again an L2 base setting. So we have E Hilbert, and we have basically a group taken multiplicatively acting on E. It is basically a solely continuous group. So and group means at one we get just the identity on E, and then we have kappa lambda and kappa lambda prime for lambda prime positive. This kappa lambda prime. Yeah, and then in our application we always have to replace lambda by either in Japanese brackets, and because it occurs so often we abbreviate things like this. Okay? And that is the definition. So basically we get the edge solar space Ws as is the regularity Rd with values in E. This consists of all temper distributions on Rd with values in E, such that that expression is finite. Yeah, so we take the Fourier transform, because then we get, so after Fourier transform in the y variables, we get a temper distribution taking still values in E. On E we have our group acting, so we just take the inverse of that. Then we wanted that here, so that this guy is locally in L2 with values in E. We basically take the E norm in E, square it, and then we have this usual factor of either the 2s. Yeah, and then basically if we so that is finite, then on that space this apparently gives the square root of that is a norm, and this is a Hilbert norm. Yeah, okay, so that's the definition. And so now here it is why this is the correct thing to do. Well, to suppose we have R D plus M. Yeah, and we want to write this space as this function space as our some functions on a D taking values in HS of Rn. Of course, if we do it in a direct way, this is wrong. S Rm. Now, so suppose, so here we have in total S derivatives in every direction, and say S is positive, and in some directions we have two S derivatives altogether. Yeah, this cannot hold. But what holds is that this equals Ws Rd with values in HS Rm with the so that the Hilbert space is our space E with the correct group action. That holds. And here's a short proof of that. That is an observation. Yeah, that was Schulze's starting point. It's not here from us. That's been known for a very long time. Okay, so yeah, so for S in R, we have that relation, and the group basically acts on functions depending on x, and it is like that. So we are stretching in the x variable, and we get the correct prefactor. This is lambda m to the lambda to the m over 2, and this lambda m over 2 is just shows in a way that there's also some guiding principle. So this group here is strongly continuous and unitary on L2. That's typically this is easily checked. That is just gives you the factor here. That's gross. And here's the proof. So okay, a quick computation shows you. So if you take the Fourier transform with respect to the x variables, sign, then it's sort of the Fourier transform commutes with a group action instead of in which way I've written it. It's proper lambda, and then you have proper lambda to the inverse of that. It's just direct computation. That is computed. It's just also a consequence, if you like, of Plancherel and the property that it is unitary enough to. So, and then the computation goes as follows. So we start here. We could start at either side. Also here I have, there was no space left. So what is missing is here our last line. That is a norm squared in that space. So you could start here, yeah, on that side, whatever you prefer. So we start here, say, with the norm, the HS norm on in Rm plus T. Okay, and then there is something like, let me write it here, and then we give it. Those are the covariables to x and y. So this is an n-dimensional variable, this is an d-dimensional variable. So we raise it to the corresponding power, and that here is the Fourier transform in both variables, yeah, x and y. Okay, so that is square of the norm, the constants. And then here comes the trick. So if you have, so that is a very useful trick. And it applies in many situations. Now I have to do it the correct way. Basically, you just pull that here out. That is here square is 1 plus psi squared eta squared. Then you just write it. It's basically 1 plus eta squared, so the square of that one, and here we are left with so I divided here with 1 plus and here you get psi eta squared. It's a very simple observation, and but it's a very useful one. And then, oops, sorry, no, and then we change coordinates. So basically, psi divided by either in brackets gets replaced by psi. There's another variable, then we just rename it back to psi. Then you get this here, and then but we get also a prefactor. That's an m-dimensional variable, so we get an eta to the m. But because of that squared, it becomes an eta to the m over 2. Yeah, inside the absolute value, and you get here psi times eta. It's just a change of variables, and so and then just compute it as an iterated integral. I can do that. So and then here, what we have in the inner integral. So here we have just the group acting on the psi variable. Okay. And then basically I use that property with lambda being either in brackets, and so just pull it out, you get it to the other side. It becomes kappa eta to the negative 1, as we can see here. Okay, and when what is left is basically the HS norm. Yeah, exactly what is written here. And here it is only I use just the same symbol here. It's only the Fourier, what we use here is just the Fourier transform with respect to the y values. Yeah, so that hat is different from this hat. Yeah, but this is exactly the norm which was given before. That is the norm in the W in the space W S as well as in H as well as to that convention. Okay. So that's basically the only the only observation we need to pass to higher dimensions. Okay, so here are a few more examples. If we have the space HS naught, so we had it yesterday, but I can just record things. So, as direct consequences, so we have HS naught 1 plus B plus the space of all U in HS of space that is supported in the closed half space. Okay? So that is the closed the closed subspace of that space, and basically this reasoning from the previous page that carries about to that space. And then that's just a quotient space here. And that's just that space is a quotient of that space and the corresponding quantum space. So it gets properties there as well. That is our standard spaces. But we had also our so we had also introduced yesterday these spaces. And they are basically, after suitable changes, they are abstract edge solar spaces as well. So let me just recall we had here was minus sine x to 0. Sorry, I multiplied by sine x to 0. Then we get s delta plus rho, and we get some other asymptotic type which can effectively And let me also recall that we have h at 0 with empty asymptotic type. This is space HS VHS. Okay, so we have the two things we already know. So so basically we get that this our space HS delta P is the WH WS, this values in the corresponding HS delta P space are on the half line. The only thing I defined here things in here that it is just a standard space, HS space for large X. That was just for convenience, yeah, because that is what one usually does. So we need to. Where is something?
There is a colors. You mean?
Yes.
We don't have colors.
Okay, that's unfortunate, but okay. So here's the change. So that function psi, that was psi of x was x for x. And this was just 1 for x plus. Yeah? So something like that. No, it's fine.
No, I mean we have colors, but the problem is that you
don't
cannot
have to get it. It's fine.
You cannot see in the recording the colors.
I can follow my talks and it's fine. It's just stay, please.
But people won't see the thing. Yeah, I mean.
Like online, you don't see the colors, so that is the problem why we only have white chalks here. But there are plenty of colors, yeah.
So basically, that this result holds. We have to just multiply that by x to the row. Yeah, so this, which means effectively, so here this was the requirement that 1 minus phi was such a cutoff function, u belongs to HS, and the other place it belongs to x to the delta hs. It's just a marginal change. Actually, my point is that we want to find, first of all, we need that result to get continuity of our operators. But another thing is we want to get the correct trace spaces. And we will see that, I just made a preliminary definition of the traces. That space turns out to be slightly too small if you have logarithmic terms. Yeah, but it's just there to get the correct thing out. Okay. Okay, so basically, yeah, so this is space as defined before. This holds where that is the group action. Yeah, so we are now in a one-dimensional situation, and we have the same group as before, lambda to the 1/2. Before it was lambda to the m over 2, m being the dimension, which is now 1, but then now we have in addition the delta, and therefore we get a minus delta here. Because I need it in the proof, I need to distinguish between delta being delta and delta being 0, I just put it into the notation. Okay? So this can be proved directly, or we can just use the result we already know, namely that this result is true for delta equals 0. Also, first of all, I should say, okay, we can just assume that we have the empty asymptotic type. So what I wanted to do here, I think I wanted just to show the changes in this and then this becomes all. Okay, that is the necessary change. Thanks. Okay. Okay, yeah, so the first observation is we don't have to care about the asymptotics. The asymptotics are handled on the next slide. And okay, so then we can assume that we have no asymptotic, so the empty asymptotic type. And then we want to prove that in that case. And basically, we just use here, as it just was written, that z space is x to the delta times z space, but z space is here the space we had before, where we already know the result. Yeah, so we then use the fact that the result is known here, and then we use that very simple observation. It is just an observation is the following. That observation is just okay. So yeah, I have maybe I should have written one line more here. It was particularly apparently. We have the v and the h as delta O. So it is just here coming from here. It's just x to the minus delta upper lambda is a delta v, and then it has O space or up to constant, yeah, and that is now actually this to commute, yeah, and that is just lambda O. You can directly change. Basically, you can just commute it through, and then this delta becomes a 0, and that's it. Okay. Yeah, and then basically we are done. So then we start here with that norm. We multiply by x to the minus delta. We get things at that norm. Then we just write what that is. Yeah, so basically, here we use the fact that we know the result for that space, and we write it as an WS space, or edge space. And that is the correct group action. That is when here acting on that function. So the Fourier transform is again with respect to the y values. Okay, and then we just use here this observation. Now we get it to the other side, and then we have basically here no, that's it. Yeah, that's it. But this is just the norm in the WS space with values in H S delta O. We could also have given direct proof that is also possible. Yeah? Okay, so our spaces are abstract edge-degenerate spaces. And that is good. So why is it good? Because of the so now first more examples. Now we come to the space. So we have so if you have basically if you have some p in our asymptotic type, say multiplicity is mp, then we get the on R plus on 0 infinity we have basically asymptotic expansions like that. So we have x minus p, we have here the first coefficient, which is in C, then we have that's the opposite. I wrote it as a minus of x. We got something like mp minus 1. Okay? Log mp minus 1x, and then we have this other mp minus 1. Now we get such asymptotic expansions. Here's x minus p. Yeah, that is what we get, and now basically we get here a trace map, which is just basically assigning all these NP coefficients, V0, V1, and so on. Okay, and we want to know what basically in which space. Yeah? What is a trace space? And actually, the trace space is also an abstract solar space. This W S prime, where S prime is S plus the real part of P plus delta by x1 half, it's just computation. But here the point is, so here we have this vector in Cm P. So this is wrong here, and it must be Cmp, where M is empty. And we have here a certain group acting, and the group acting is just a matrix group. And the matrix group is like that. It has it is upper triangular matrices. So and along the main diagonal we have 1s, and then we have minus log L minus log sorry lambda. Along the next diagonal, then we have lambda, along the next diagonal, and so on. You all have seen that matrix. ODE course, solving ODEs with constant coefficients. Okay, that is basically so just so I'll tell you on the next slide here. So we take the Jordan block of size mp belonging to the eigenvalue 0. So the eigenvalue is along the main diagonal. And I guess I call that is called super diagonal. I don't know. We have ones in that place, and zeros everywhere else. And if the eigenvalue is 0, then that is a Newtonian matrix. So we have J and power mp is 0. Yeah, you square it. The ones you can just always move once, and then find it almost completely. So you can easily compute stuff like e to the e dj. So t being time, and you have your say ordinary differential operator with constant coefficients, you want to solve it, you put it into a first order matrix form. Then you basically, the matrix form, you just put it into the Jordan form, then you get a block diagonal matrix with Jordan blocks along the diagonal. And then basically you have to compute the exponential of that matrix, which is just amounts to compute that. So eigenvalue is 0, then you get here just finally many terms. And that's just what you get. And what we have is basically lambda to the minus g, is e to the minus log lambda j, and that is just time. You get exactly what is written there. And actually you also get basically that these matrices form a group from that. These matrices form a group, and this basically what we need to know. Okay, so basically then so I will show you a little bit later how that works, just when we derive regularity properties of the traces. Yeah, I will give the corresponding arguments later. That discussed, yeah, in a moment. So now we had defined here our traces. So here, if there's no logarithm, we set it is in HS. Then if there's one logarithm, then it's in HS. Here's 1. And so that was here the definition. Maybe what our definition as not either being so in this space here used before, it's just more convenient to work. This one is just slightly smaller. This illusion. Okay. So now why is this reformulation as edge context useful? Well, we not only have spaces, we have also operators. And operators is, so we have a second Hilbert space, and we have operators taking values, now unbounded operators from Hilbert space E to Hilbert space E2. So this still is not the value transform. Yeah? There's not so many different ways to notate things. It's just it's a second Hilbert space with another group action. And then we want Z A to be smooth for the strong operator topology. And then we say that this A belongs to our symbol space SM, and here basically Z and the tilde implicitly come with these group actions. Yeah, that's part of the setup. If and only if, so that this also here we have the standard estimate, but then things get twisted by the group action. Yeah, and basically, if you look into this definition, you get something like that. Over here, and then goes U, either E, either. So here, these this couple either to the right compensates here for this couple either linear one, which is sort of cancels each other, and here is the group action 3 entities. So that definition we have a chance to do the correct thing, and actually that's it. This is just what it's doing. Next slide. So we have not many later. So first examples. So we have another, but we have also homogeneous R symbols, and so to the sort of twisted homogeneity. So now things are defined for either different from 0, and we multiply by a positive factor, the covariance. So here without these group actions, we would have just the usual thing, right? So it's just homogeneity. But now, because we have the kappa here and the kappa tilde here, we need to sort of compensate for that. So we have kappa lambda to negative 1 here and kappa lambda tilde here. And then it's basically a simple observation. Yeah. So if you, we have usually we will be having your 0 at the origin. We cut out that 0, yeah, and then we get an amplitude function in that space. Okay. This is just the usual arguments. The usual arguments work. Okay. So now what is why is this convenient? Well, there's one example. I think that's an impressive one. Our trace operator, so gamma p, this was just this vector here. Gamma p1, gamma p and p minus 1 is homogeneous in that sense of degree 1/2 minus p minus delta. Yeah. So we have here, yeah, we have the kappa lambda. So it's actually, it goes from, yeah, so this gamma p goes from HS, well, I mean, yeah, p and S. Plus into CMP. Yeah, and on CMP we have here Z group action, that was before, and on Z space we have the group action with the so here lambda dx lambda minus delta. Okay, so this guy is homogeneous. Yeah, and basically we have to have enough regularity. Yeah, in order to formulate that, we have to have enough regularity. Yes, that's all. Yeah, and sorry. So that is sorry. That is a homogeneous function, but it's basically it's independent of y and eta. So here no cutoff function is needed. Okay, therefore the whole operator is already in that simple space as a consequence of that. As a consequence of the homogeneity. Provided we can just define the space operator, and we can define it as it's large enough and as large as that. Okay, this is simple proof. So basically, see formally, I just write the stuff we are interested in. Oops. Yeah, so I write just here. That is the part of the algorithm we are interested in, and all the rest is of no concern to us at the moment. Yeah, so that is here standard arithmetic terms, and here we have complex numbers. Okay. So then we just compute kappa lambda to the negative 1 of v. Here is the group. If we have here 1 over lambda, then comes to lambda to the delta minus 1/2. We have it here. Then we get from the x to the minus p, and we plug in lambda to the negative 1, so we get a lambda to p. And then basically all the rest is basically unaltered for. So and then it starts here, and then we get where this p lambda group comes in. Because now we just need to basically just do it here for yeah. So then we need to write here this log square of lambda to the negative 1x that we write as a log x minus log lambda squared, and this is then log x squared minus 2 log lambda log x plus squared. Right? So here we have a term with a log squared. Here it just adds to the term where we have only logarithm. And here just this adds to the term where we have no logarithm. And if you write out the whole thing, then and then just take the corresponding traces. So basically, taking traces means to read out the coefficients. So we start here with those coefficients, and the new coefficients they are just determined in that way. But you can just do the computation and examples. So proof in general, and that is just that is here just so that is here gamma PV, and that is here P pi lambda to -1. So basically, the pi lambda had also here the pi lambda was not lambda to the j, but lambda to -j. So what we have here is pi lambda to -1, then we just get here that stuff here to the other side, both of them. That is the homogeneity. Our traces are homogeneous. This is homogeneity, and this comes in very handy. Because so just let me just the consequence of that is that gamma p belongs to that. Maybe just put it here. So gamma p is 1/2 minus the real part of t minus delta. So it's independent of y and it's independent of y and either, and then this is from h as t lambda plus t, and this is for s. This is 1/2. So here, obviously that number has to be positive. S minus n has to be positive. Okay. So that's the result. So, and now comes here the next result. Xylem. So basically, Schulze had knew it locally. The global proof, the global result was given by Xylem 99. And basically, you have an operator in here, and then you basically quantize it in the usual way. Just use the Fourier transform in the y variables. And then your operator usually is written that way, and then it acts continuously from WS, this values in E, to WS minus M, this values in E tilde, ES. So I'm not going to prove that. It's a really longer proof, but this has been proven and can be used, of course. So now, you recall that thing, and we recall that our spaces are vegetable spaces. So then we get it for free that gamma p takes h as delta, this asymptotics of type p, so on the half space to that space. Where S prime is just that number here. So that means this number has to be positive. So that is just a condition. Now, so for instance, if you have gamma naught plus 3 x equals 0, you get it basically for free. But gamma naught on that space. And maps to h s minus 1/2 for s minus 1/2. Same for the normal traces and so on. That's just it's just provided by the theory. Once you have realized that your spaces have like vegetable spaces, and that this is just here homogeneous of the corresponding degree. Okay, it's delta is 0, p is 0, so that's a symbol of order 1/2. So So it lowers the order by 1. Okay. So I still have a few minutes left before I start the next slide. I just wanted to make a general remark. So these edge techniques, they are seem to be very that they can be applied just in that situation. That's a particular, it's just particularly adapted to that situation. This is not true. That is not true at all. And I just want to use few minutes to show you another example. Basically, that means keep your eyes open. This is just you all know the Tricomi operator. You have a one-dimensional variable x, x and r, y and rd. Okay. And the operator is dx squared x Laplacian of dy, which is an elliptic for x positive and hyperbolic for x negative. So, and you can just start making our theory also for that operator. And so basically, so basically, what happens here is basically to pass smoothly. So here's separating interface to pass smoothly from the elliptic to the hyperbolic side, or the other way around. But sure. And this is only possible if the coefficients. So we want to have smooth coefficients if the coefficients degenerate at x equals 0. But this degeneracy is not arbitrary. That is, and so basically, that degeneracy is also formed. So we start with we have a parameter involved. This is a rational number, positive. So you want to have a rational number that you have basically elliptic differential operator calculus. Otherwise, it's not really essential that it's rational. But I mean, if you want, you can suppose it's useful also. Okay, so and here in that case, this parameter is 1/2. That's a positive rational number. And then the operators, they are also formed to degeneracy. I'm not discussing elliptic hyperbolic, I just discuss the degeneracy. And this operator is also formed a plus alpha is at most, and then we have here certain smooth coefficients, and then we have these covers dxj d alpha y. And where what is kj alpha? So kj alpha is a natural number or 0. This is just that you get smooth coefficients. Okay? Smallest is a property that it is at least j plus l star plus plus 1 minus times the length of alpha minus m. Yeah, so if you take the smallest, only you get integer having that property. This is the thing you put here. And you can check it that you can write it here. That here, the example L star is 1/2. That is not my point. Okay. The thing is, if I have an maybe I should keep that here. Little space. If I have an edge-degenerate operator, it is of that form: x, y, x, dx, x, y. Yeah, and now if you look carefully, so it's formally also formed. Now our operator becomes x to the minus m dxy. and then you have x to the L star plus 1 dy. This is essentially also the same form. Okay, here we have the L star times alpha equals here. Here we have the J and we have something else. So then also here this H philosophy applies. Actually, with the group kappa lambda v of x, so here it is something. But here the point is to take lambda 1 over x plus 1x. That is the only change. Yeah, actually you can check if L star is 0 if you go back to this standard situation. And then you get also, having as an operator, you get also the principal symbols. Yeah? So two principal symbols we have. We get this two principal symbols. And psi, x, y, psi either. Here you just take all terms where j plus alpha equals m. And then you have your a, j alpha, x, y, x to the k, j alpha, psi j, e alpha. But we also get this what in that context I don't call it boundary symbol, but I just use the notation and go into these new notation that is as before operators. Now with polynomial coefficients, these differential operators, with polynomial coefficients in x on all of R. So it's basically, so here you keep you keep z, but you make z an equality. And you want that to obtain j alpha is j plus L star. Or put it differently, you want that to be, in that particular case, to find this secondary principal symbol, you want that to be a non-negative integer. And then you do the same thing as before. You freeze coefficients here. We can depend on y, that is fine. You keep that. You take j alpha is now this guy here. I'm just operating with that. And then you have here dxj beta alpha. And what then happens is that so after
So it depends on x's.
this operator this takes the values in ordinary differential operators on R with polynomial coefficients. It's operator value, but as an operator function, it depends on the point of the basically the cotangent bundle or the separating interface. Yeah, and then you basically you have that, we have x and we have the modulus of either. And you get the two curves. This curve is something plus either is 1 or 2, it doesn't matter. Things up here and down here are controlled by the principal symbol. And things in this transition zone are controlled by that symbol. So if you pass from elliptic to hyperbolic, you input this side. It's the same thing as before. It is an abstract edge equation. You can apply the techniques and so actually we did, yeah? Partly in cooperation with Australia. Okay. Yeah, but it's just okay, general observation. Okay, so I have 5 minutes left. Maybe if there are questions I can answer, or I start the new one here.
So when you played this with Drea, this was a while ago, but
A while ago, yeah.
can you also use this the edge spaces and
Yes. This was basically the way to come up with separate spaces. So basically, we have two principal symbols, and like in this other edge case, our spaces depend on two parameters, S and delta. And so if you have, if you are in the hyperbolic relation, you let x to be t, that's time. You have a degeneracy at t equals 0, you impose a Cauchy data 0, then you observe loss of regularity and passing from Cauchy data to the solution, as compared to the sinus relation. Yeah? And this loss of regularity is reflected by the second parameter. And this technique, basically, later you just deformulated the spaces, yeah? But to find the spaces, was just using this edge philosophy. Yeah, once you have the correct definition, of course, you can reformulate it in many other ways, yeah? Okay, I just wanted to say, yeah, these techniques are not specific to that problem, but they are more general. Okay, so now, edge operators is
could be a good moment for.
or we make we make a break and then I continue.
It's a new topic.
Yes,
It doesn't make sense to talk about it.
yes, I absolutely agree.
Okay, so
Yes. It's a similar idea that you saw the example position of this open space that you introduced,
Yeah.
or Euclidean space, something mentioned, when they coincide with the classical ones,
Yeah.
or Euclidean space of higher dimension.
Say again?
I mean, this WS
Yeah.
or
Yes, yes.
RD was equal to HS,
Yes.
RD plus something.
Yes, yes.
Can you maybe make a comment on this, because I don't really understand how.
No, I mean, basically, I want
It's higher dimension.
so part of the edge philosophy is we have okay. That's actually a good question. Basically, so we have our I draw a real edge that you see what I mean. Yeah, so, we have a very particular case. So our cones are not that complicated. Yeah, but I draw it. Yeah, so basically, to get our calculus now. Yeah, so we take operator functions depending on the buying either here in the Coulomb bundle or the edge, which is locally is basically it's an RD, yeah, to be in space, and it takes values in these cone-degenerate operators we have previously defined. And to get our full calculus now, we essentially do that. We have A y eta. Yeah, so then we get basically our things also acting pseudodifferentially with respect to variables. So that is what we're going to do. But then if we basically split operators in that way, we also want to split the function space in that way. So now our functions depend on x and y, and we want to write it as basically functions of y taking values in the spaces these operators are acting upon. Yeah, that is, yeah, and basically, first thing where this should work is, of course, dimensional space. And then we cannot do it here. We cannot, because this introductory example. That would be the naive way to do it like that, but this is not going to work. Right? But it works if you just put WS here. Yeah, that was just, yeah, that was. You want to write it as a function of y taking values in a space where you already know that the operators here act on. That's the whole idea. Yeah, that we have just. I just I just did it the other way around. I first introduced the spaces and the abstract operators.
Okay.
This explains well the idea.
Yeah.
Okay, so we have 15 minutes break.